far over. Our next presenter is Riya, and I am so glad that we had somebody who really likes meteorology and atmospheric science in the cohort this year. Last year we had one or two, but this year it's been great to see Riya talk about stuff like the North Atlantic Oscillation, and I think even maybe some atmospheric rivers or the Madden-Julian Oscillation, all sorts of cool climate dynamic-y oscillation-y type stuff. So it's been really fun. Riya has really found a project here that I think that she was the best person to do, because she gets the science, but she's also just like incredibly likable and engaging, and to do an interview project like this and synthesize this complicated information into something, a digestible, deliverable, is pretty impressive, because this brings together astrophysics, atmospheric physics, and then gives the people who do all of this work an opportunity to tell their stories. So, Riya, I think this was a really awesome project, and it's all you.
Thank you so much, Corey. You're gonna make me a little bit emotional. Like, woo. Okay, I'm good. Okay, let me just pull this up really quickly. Okay. Hi, everybody. Thank you for joining us today. I am so excited to talk to you guys today about the sun's true role in climate change. This is an educational video, a joint project with NASA's Solar Radiance Science team. Just to get us all on the same page here, real quick. Is the sun to blame for climate change? Nope, it is not to blame for climate change, but the sun is one of the many drivers of our climate system. So we'll get into a little bit more detail about how that actually works. So where are we with public understanding? Well, the basics of climate change are generally well understood by the public. For example, if you pump CO2 in the atmosphere, you trap heat and increase the overall temperature of the Earth. But as the number and complexity of climate change drivers are studied and brought to public attention, there is growing confusion about what the most important driver is. Is the sun the mightiest thing, and is that going to overpower every other driver in the climate system? This allows for misinterpretation and deliberate misinformation. Earlier this academic year, it was leaked that the Heartland Institute, which is an organization notorious for its stance that opposes topics with scientific consensus, who are planning to publish a teacher-targeted reading that incorrectly blames the sun for climate change. So they're able to do this because the science surrounding the climate system is incredibly complex. So we decided to create an educational video. We cover first the historical moderate minimum, which is a period of low solar activity. We then go into the scientific background on the sun and its impacts on our climate. From there, we interview NASA Solar Radiance Science Team, or SIST, researchers and learn about their previous findings and current research, and end the video talking about the implications of a future solar cycle on climate change. So our goal is to showcase this video on the Sun Climate Research Center website, collaboration between CU Boulder and NASA Goddard Space Flight Center, and also to submit this to teacher resources web pages as a direct response to the Heartland Institute's potential publication. So for the rest of this presentation, I'm going to give a lecture on the scientific background. So it will be kind of following the video content that we have planned. So it is currently in progress and will continue to be in progress during the summer. So let's start as far from us as possible, the sun. So the sun has multiple cycles, the shortest of which is an 11-year cycle associated with reversals of the sun's magnetic field. This creates sunspots, which are dark areas on the surface of the sun, which are areas of reduced surface temperature. Accompanying these sunspots are bright white blotches called faculae. Faculae overpower the dimming effect of the sunspots to overall increase the total brightness of the sun. So periods of low solar activity are called solar minimums, and high solar activity are called solar maximums. Basically, if you have a solar minimum, you have reduced solar activity and thus reduced overall brightness of the sun. If you have a maxima, you have increased activity and increased brightness of the sun. So we have that 11-year cycle called the Schwabe cycle. This has changes in brightness by about 0.1% between solar minima and maxima. But we also see that over these 11-year cycles sits numerous other cycles. Most relevant to us currently is the 100-year Gleisberg cycle, but additionally there is a 200 and 2400-year cycle. Alongside the longer cycles, the Gleisberg cycle modulates the Schwabe cycle, weakening and strengthening it over the century. So now let's move a little bit closer to home. The climate of the Earth, as defined by its surface temperature, is a balance of incoming and outgoing radiation. So incoming solar radiation is primarily at visible wavelengths, which is why when we all went out to lunch, we had to put our sunglasses on. The outgoing radiation from the Earth instead is at infrared wavelengths. So infrared is what we can think of as heat. So you can't see it, but if you put your hand over a coffee cup, you can feel the heat radiating off of it at infrared wavelengths. So the incoming solar radiation comes primarily at the equator to the Earth. But the outgoing radiation from the Earth is happening at all latitudes equally. Basically what happens is this creates an imbalance of the heat energy on the planet. So you have a surplus at the equatorial regions where most of the sunlight is coming in, and you have a deficit at the poles where you get weaker, where the sun is weaker. And so the climate system has to somehow move this energy from the equator to the poles to balance out this imbalance. And the way it does that is through dynamical motions. So at the heated equatorial regions, heat rises up and moves towards the poles. And this generates a series of circulation cells. You may have heard of the Hadley-Farrell and polar cells. But this is not the only method of heat transfer, because the Earth is not at a standstill. It's moving at about 1,000 miles per hour. So what this rotation does is creates these dynamical turbulent motion that is related to the weather that we see today. So if you imagine a rotating hurricane. So together, the circulation cells plus the dynamical and turbulent motions of the atmosphere that arise from the Earth's rotation ultimately set up our climate and transfer this heat energy to the poles. So in a very simplistic sense, someone might think that, well, if the sun's energy changes, maybe the surface temperature on the Earth will increase everywhere, right? It's heating up the whole Earth. But that's not the case. Instead, changes in the energy actually alter the dynamical motions of our atmosphere, and this can be for changes in solar radiation or from trapped heat from greenhouse gases. What this does is it disrupts the distribution and transfer of energy from the equator to the poles, particularly affecting the mid-latitudes where these circulation cells interact. So this is what gives us such differing responses across the globe. For example, during solar cycle 23, there was an increase in the global average temperature by 0.1 degrees C, and we saw drought in Western Europe, warming in the North Atlantic, and cooling and higher rainfall rates in Oman. So the pattern is not uniform, but we can expect changes in solar radiation, just like El Nino, volcanic activity, and greenhouse gases, to have its own effects on the Earth's climate. So the change in global average temperature between solar minima and maxima is estimated between 0.05 and 0.1 degrees centigrade. For comparison, the anthropogenic effects over the last few hundred years are maybe 6 to 7 times larger than that. And that is because the sun is cycling, while greenhouse gases, as shown in graph C, are increasing monotonically. So basically what we see in the Earth's surface temperature in response to changes from the sun's brightness is small, quite small compared to the effects of anthropogenic emissions. So next, let's take a look at the best historical example that shows us the effects of decreased solar brightness. The Maunder Minimum was a period of prolonged low sunspot activity and lasted for about 70 years. This period coincided with a part of the Little Ice Age, which is a period of cooling affecting parts of the globe that lasted in total 300 years. During the Maunder Minimum, we saw the freezing of seas and rivers in Europe, glaciers encroaching on Swiss towns and farms, and crop failures that caused changes to farming practices all across Europe. And it's important to note that the Maunder Minimum did not cause the Little Ice Age. In fact, the effects of reduced solar activity impacted the North Atlantic Oscillation in ways that not only caused cooling over Europe, but also warming over parts of the Arctic. And thus the Maunder Minimum is a slightly Eurocentricized event, as artwork like the one shown up at the top there depicted freezing seas and frost fairs in Europe, while art from more warmed places is lacking. So although the Little Ice Age was a background event occurring during the Maunder Minimum, the impact of solar brightness did not solely cause global cooling. It's actually estimated that it was volcanic activity that first set up the little ice age, and then the impacts of reduced solar brightness contributed to that cooling. So why exactly did the moderate minimum occur? So we need to first consider one of the most important atmospheric cycles for Europe, or the North Atlantic Oscillation, NAO. The NAO is defined by alternating surface air pressure between the semi-permanent Icelandic low and Azores high. During an NAO positive index, these pressures are very high and very, very low respectively, and this brings warm and moist conditions over Europe. During an NAO negative index, these pressures show less contrast. This allows Arctic air to flow over northern Europe, bringing cooler conditions to the region. But this also allows warm air to flow over regions from the Hudson Bay to Greenland. So the North Atlantic Oscillation is one of many oscillations on our planet. For example, we're all probably more familiar with El Niño Southern Oscillation here in California. And it's important to note that the NAO is not the only oscillation affected by changes in the sun's radiation. We've just chosen to cover the NAO because it's most relevant to the Maunder minimum, which is just such a stellar example of changes in solar radiation. So how exactly does the sun's radiation impact our atmosphere? Well, the sun's UV radiation breaks apart oxygen molecules in the atmosphere, which recombine to then form ozone. So we go from O2 to two separate oxygen molecules, which then recombine with other oxygen molecules to create O3. This creates the ozone layer that protects us from harmful UV radiation, basically the world's most effective sunscreen. And this warms the stratosphere, and this temperature increase with height puts a cap on the weather that we experience. So most of the weather that we experience is confined to the lower levels of the atmosphere in the troposphere where we live. So as the sun's energy decreases during a solar minimum, there will be less ozone creation from the UV radiation in the stratosphere, and thus cooler temperatures in the stratosphere. At the same time, as we increase greenhouse gases in the troposphere, you have increased warming in the troposphere. So what we're seeing is basically a shift in altered temperature and density structure in our atmosphere during a solar minimum. And what this does is shift the NAO into a negative index. So that's what is hypothesized to have been seen during the Maunder minimum, was a shift into the negative index of the NAO, which allowed for these cold, dry conditions to be set up over Europe. So what about climate change in conjunction with future solar cycles? Do we expect to go into another solar minimum in the next century? And if we do go into another Maunder minimum, is the sun really going to save us from our warming climate? To answer these questions, it's crucial to continue observations of the sun to understand the impacts that it will have on our climate in the future. So we did talk a little bit about the Gleisberg cycle earlier on, which is that 100-year cycle that's modulating the 11-year Schwabe cycle. In the last 20 years or so, we've been in a period of low solar activity. And this has caused speculation that we may enter into another Maunder minimum-like event with drastic changes to our climate. And there's also been speculation that this may offset the climate warming that's been caused by our anthropogenic emissions. According to Dr. Judith Lean at the NASA Solar Radiance Science Team, we may instead be seeing a ramp up into another Gleisberg cycle. So we were at the low of this cycle in the last few decades. So as this cycle ramps up, the 11-year Schwabe cycle will also follow, and basically the range of solar brightness will thus be increased. So scientists are increasingly predicting that rather than decreasing brightness, the sun actually may be getting brighter. So just to finish this off, I mentioned that this is a video project. It is still in progress, but I do have a little clip to kind of show what we've been working on for the past couple months. And that's an unfortunate goodness. Let me go to, I might drop. Thank you. Let me do it from there. That's such an unfortunate thumbnail. I should change that. Okay.
Now, there's been some speculation that if the sun was to go into a Maunder minimum, that would somehow save us from global warming. And that's so far from the truth that it needs to be pointed out that were the sun to go into a Maunder minimum, we would only see a decrease of about less than 1/10 of a degree centigrade. So that is a factor of maybe 10 less than we expect to see due to greenhouse warming over maybe the next 40 years. So for the immediate future, we can expect warming, warming, warming.
The sun is not an easy answer to reverse the impacts that our fossil fuel emissions have had on the climate. But addressing climate change provides us with this golden opportunity to better understand the sun and its impacts on our climate in the future. Our obligation to this planet still remains to reduce our emissions and pass along a fully habitable world to future generations. Thanks for joining us. And just to finish it off, thank you so much to my committee. Dan, Lauren, Cheryl, Jane, you guys have been incredibly helpful this entire year. Thank you so much for all of your support. And of course, the cohort for just being the best friends I could possibly have in this program. Thanks, guys. Happy to take any questions.
So I guess I know that the purpose of the video was to kind of counter misinformation. I'm assuming amongst school-age kids, because you were saying that it was for a teacher's resource. Mm-hmm. Is there any specific tactics that you use to counter misinformation among climate change?
Yeah, so actually when we decided to create this video, we thought a lot about what this target audience should be like. So a lot of this content is very complex, and so my kind of portion of this video was to take this complex science and break it down into smaller bite-sized pieces. And so, but at the same time, the knowledge of the sun's effects on our climate is also generally not well known in kind of our climate science sphere. I definitely didn't really know about it, and I've been in the climate science sphere for 8 years or so now. And so I also received kind of a general consensus from my cohort as well that they didn't quite understand what the effects were. And so what we decided to do for this video is that we have 3 interviews with Dr. Dan Lubin, who is my chair, Dr. Odell Coddington, and Dr. Judith Lean, and all of them are from the NASA Solar Radiance Science team. And so they get to talk about their research. And so we based the scientific content on what they were also interested in talking about. So the video is kind of in 2 parts. The first part is the basics of the science and is kind of angled towards a younger audience, an audience that knows a little bit less. And then for those who are interested in knowing more about the the current research and what their findings were, that's what the second part of the video is for with the interviews. Yeah, that was sort of the tactic we used.
Thanks so much, Riya, and thank you for the wonderful video preview too. I'm excited to see the full thing. You mentioned integrating it into teaching output, essentially. Were you considering through traditional classroom methods, or were you looking more at online platforms such as Khan Academy? I know NASA has paired with them in the past.
I'm so sorry. Could you repeat that? I actually
I'm sorry.
I can't hear it.
No worries. I'm sorry. Quiet voice. I was saying thank you so much for the video. I'm excited to see the full thing. And were you looking at pairing this with traditional teaching methods, such as viewing it in classrooms around the United States, say? Or were you looking at perhaps putting it into online platforms, like, for example, Khan Academy? Are you considering both? Or?
That's a really interesting thought. I think we were mostly considering kind of the first route so far, but I think that's still kind of, we could definitely consider putting it into an online platform. I think the goal was to get it up onto YouTube being the easiest method of distribution, and then having it on these teacher resources web pages like the one at SIO and at Sire's Education in Colorado, having it up on there so that it's available for teachers who want to put it into their curriculum. So, but I think that's a really good thing to think about. Thank you. Yeah.
Thank you.
quick one here, I think. This is a extremely dense topic and lots of deep science too. And I mean, even this was a great summary that you provided us, and it was still like, wow. For a film like this to put forth, I'm interested to see what the final is going to look like. But at the same token, will there be, perhaps in a YouTube description, an extra list of resources that people can go to learn more about specific topics and different aspects? And can you speak a little bit to the types of things you're putting together for that?
Yeah, absolutely. I think probably one of the most useful things is that this topic covers a range. You even saw it in my video, it was like solar cycles, we've got North Atlantic Oscillation, we've got all these different pieces to the climate system. And I think that would be really useful then to have, I'm sure, like, probably tons of videos exist out there. I've definitely seen the NASA ones about the solar cycles. So to have those linked in the description, I think would be the perfect way to have somebody who maybe wants a little bit more information than we're able to dive into in our 20-minute total video to be able to click on that and then go learn a little bit more. Yeah, so definitely.